One of the primary sources of both inspiration and information throughout all of the vacuum tube projects that I've been doing up to now has been the old IBM vacuum tube computers and calculators from the 50s and 60s. I think these are just really beautiful machines, and they have really innovative engineering techniques behind them. And I would love someday to get my hands on an old IBM calculator like the IBM 604. But of course that's well beyond the realm of possibility. Those are extremely rare, and if you ever do find one, it's extremely expensive. But that doesn't stop me from keeping my eye out on eBay anyways. And the IBM 604 and 605 and even the 700 series used these really interesting pluggable modules. And so while the full machines, of course, never show up on eBay, those modules sometimes do. And I always keep an eye out for them. And there was one recently on eBay that really piqued my interest, and so I bought it. And that's this little guy here. And it came just like this. There were no tubes in it, and well, there's very little components on it. As a matter of fact, there's only 2 resistors and a handful of wires. But this one was really unique because it holds 2 vacuum tubes, one of which is upside down. And furthermore, it holds both a 7-pin and a 9-pin vacuum tube. But the seller had no real information about this. And there was no even information about which particular IBM machine it was out of. And so I thought it was super interesting and I couldn't pass up on it. So I purchased it and it's here. And well, my goal today is to figure out what this thing does and maybe put some tubes in it and maybe even plug it into something and see if we can't get it to work. But the first step to figuring all of that out is to sit down and trace out what all of these little individual wires do and where they go to here. And if I can trace out the pinout of all of this, then I might be able to figure out what kind of tubes are supposed to go in here. And if I can figure out what tubes are supposed to go in here, well then we can write down the schematic and maybe figure out what ultimately this thing does. So let's hop over to the bench and start tracing out wires, and maybe we can figure out what this thing does. Well, I'm pretty happy with how tracing all those different wires turned out. I'll go through and explain very briefly what we've got going on here. Down here on the bottom, we've got our 10-pin connector that's on the bottom of the module. And then we have, in the middle here, we've got the 7-pin tube. And then on the top, we've got the 9-pin tube. And so I actually have a little extra information here. You can see I've got 6AL5 and 6201 written down here. And that's just because by looking at the way that this was all laid out, I was able to figure out what kind of tubes were supposed to go into both of these sockets. And the first thing that I always keep an eye out for when trying to figure out how a random tube circuit is set up is taking a look at the heaters. And on almost every single 7-pin tube I've seen, the heaters are on pins 3 and 4. And on almost every single 9-pin tube I've seen, the heaters are on pins 4 and 5. Now with the 6-volt tubes that I've been using, like the 6DJ8 or the ECC88, again, the heater's on pins 4 and 5, but you don't tie them together. And so that kind of threw me for a loop at first, because you can see that pins 4 and 5 are tied together. So I mean, how can we power the tube if I'm supposed to have 6 volts coming into one and then ground coming out of the other to run the heater? And then I remembered that 12-volt tubes often have a center tap. And the way that works is that essentially there are 2 heaters within the tubes, and then there's a center tap in between the heaters. And so you can run 12 volts into the end of one heater and ground out of the other, and there will be a 6-volt drop across each heater because we're running the heaters in series. Or you can run 6 volts into the center tap, and ground out, pins 4 and 5, and that'll put 6 volts running through the heaters in parallel. And we can actually see that's what's going on here. So pin 9 and pin 3 are actually tied together, and they are the brown wire, and that's going to be our 6 volts. That's the 6 volts that's powering our heaters, which means that pins 4 and 5 on the 9-pin tube and pins 4 on the 7-pin tube are going to be going to ground, which threw me for a loop at first because the wire that runs to all of those is actually red, and conventional logic tells us that red is positive and black is negative, but that's not the case here. So red is ground in our situation. And the final nail in the coffin to figuring out that that red wire was indeed ground was seeing that it was also tied to pin 3 and pin 8 of the 9-pin tube. Now, I've been playing with 9-pin dual triodes long enough to kind of have the pin out of them memorized, and seeing pin 3 and pin 8 tied together as well as tied to the ground of the heaters, well, that was kind of a giveaway that this is going to be a 12-volt dual triode tube, like a 12AU7 or a 12AX7. And in this case, I ended up using a 6201, which is kind of like a specialized version of I think, a 12AT7. But in those dual triodes, pin 1 is often the plate, pin 2 is the grid for that plate, and pin 3 is the cathode for that plate, and that is one triode. And then on the other side, we have pin 6 as a plate, pin 7 as a grid, and pin 8 as a cathode. And so we can see that the two cathodes are tied together. So that must mean that those are indeed cathodes and that this is indeed a dual triode. So we've got this figured out. This is a 12-volt dual triode. And then to figure out this 7-pin tube down here, well, I kind of had an educated guess that it might end up being a diode because pin 6 here was tied to ground with everything else. And just from experience, I happened to recognize that pin 6 being tied to ground could be an internal shield for a dual diode like the 6AL5. And once I kind of guessed that it was the 6AL5, I was able to plug in, the cathode of 1, the plate of 1, the cathode of 2 and the plate of 2, and it all actually suddenly started to make sense. And so knowing all of this, I was actually able to draw out a schematic. So here is the schematic for that IBM vacuum tube module, which I think is pretty cool that we were able to figure this out just by looking at it. Now, it's a little confusing to try and figure out what's going on with this 6AL5 down here and how that interacts with the grid up here. But remember, the 6AL5 is just a diode, and it might be easier to understand if we just draw it out like a normal diode, which would be like that. All right, so instead of coming out through here and going through that, we can just imagine it going through a diode like this. All right, and so this creates kind of an interesting thought experiment to what this does. And I dug through all of the customer engineering manuals that I have, and I wasn't able to find this exact layout. And so I can really only just take a guess at what this does. But I have a pretty good idea, and in order to understand where I'm coming from, we need to actually take a look at some of the IBM customer engineering manuals that I do have. And so I've got my little notebook here, and so we'll go ahead and open this up. So I've got this split up by machine, and this first tab here is the IBM 604, and I've used it before in the past as a good reference for some of the things that we're building, in particular the practical inverter circuit. With the practical inverter circuit, we saw that we had plus 150 volts as our main voltage, and then we had a negative 100 volts as our bias voltage, and we saw a logic high and logic low swing of plus 150 to plus 50. And the more I thought about it, the more that didn't make sense to use for the module that we have. And so I did some more searching through the IBM 604 here, and they even have this wonderful list in the back of all the different vacuum tube circuits that they have. And none of them really matched up, and the voltages didn't ever really make sense for the layout that we had. But then I looked at the IBM 650. And again, just like the IBM 604, it's a fantastic customer engineering manual with a ton of just wonderful information in it. But one of the things that I found really interesting was this page here on signal level restoration using a double inverter and cathode follower. And you can see that, like the IBM 604, they're using plus 150 volts, and they're actually showing a logic high, logic low of plus 150 to plus 50 here. So that's right on par. But they're using a couple different negative voltages for biasing. And what I found really interesting was that the restored signal coming out of the other end here was plus 10 to minus 35 volts. Now, if I take this plus 10 to minus 35 and use that as an input to the circuit that we have, so if we think that maybe we have on the 4 input lines here, gray, green, purple, and blue, we have something that swings from plus 10 to minus 35. And the way this is laid out is that we can see essentially this is 2 separate circuits that don't influence each other. So we can actually divide this right down the center, and we'll just look at the left half for now. So let's assume that minus 35 is a logic low and plus 10 is a logic high. So if both the purple and the gray wire, if both of these inputs are at logic low, well, the grid is going to be pulled to essentially minus 35, which means that there's not going to be any electron flow from our cathode to our plate, which means that the black wire here, which is essentially the plate, should be at whatever B plus voltage is. Now, if we take one of these and we change it to a plus 10, well, our plate shouldn't actually change. So let's think about that. If we change the gray wire here from minus 35 to plus 10, and the way that the diode is set up is that this plus 10 is going to get essentially overwhelmed by the minus 35. And so the actual potential here at the grid should still be negative. And conversely, if we make the purple wire the plus 10 and we leave the gray wire as a minus 35, well, that plus 10 can't go up to influence the grid here because it's being stopped by the diode here. So what happens if we change both the gray wire and the purple wire to plus 10? Well, the plus 10 on the diode essentially acts as closing the door for the plus 10 from the gray to go anywhere except for the grid, pulling the grid to a higher potential and allowing electrons to flow from the cathode to the plate of our triode up here. And when that happens, the potential of the plate is pulled low to a potential that's closer to that of the cathode here, which is ground. And so that should essentially be a logic low. And so if we draw out a truth table here, so let's call U input A, and we'll call U input B, and we'll call U as our output. And we'll say that at minus 35 for both of them, our output is going to be plus 150. And then if it's minus 35 and plus 10, or plus 10 and minus 35, well, our output's not going to change. However, if both A and B go to plus 10, well, now we're going to pull the potential of this low. And we've seen that in the IBM 604 and even in the IBM 650 here, when we pull the plate low, we see that we get about plus 50 volts. All right, so if we just change this to ones and zeros, we get something really interesting here. So if we write our truth table like that, well, suddenly that makes a lot of sense. That is a NAND gate. So the output is essentially on unless both inputs are on, in which case the output is off. So my guess as to what this is that it is a dual NAND gate using a dual triode and a dual diode. So that's what I think this is. Now, I'm saying that this is a guess because I haven't found this exact circuit in any of the IBM material that I've been looking for. And I've actually been looking for this exact same module elsewhere on the internet. I can't even find any other pictures of it. So I don't really know for sure. But given the fact that we saw that a restored signal of plus 10 to minus 35 in the IBM 650 customer engineering manual, and what we know about how the triodes work, this actually makes a lot of sense. Now, I would love to actually power this up and get it to work, but I don't have all of the different voltages that are going to be needed. I mean, you can see that without having anything else, like any of the other circuits to make our restored signal, we actually need quite a lot of voltages. We need plus 6 volt for the heaters, we need plus 10 volts, we need plus 150 volts, and then we also need a minus 35 volts. That's quite a lot. But, you know, I can get plus 6 volts using one of the little buck boost converters that I have. So we can do that one. Plus 10 volts is a little more difficult, and plus 35 volts is a little more difficult. But you know what? I think as long as we have a positive voltage and a negative voltage here, they don't have to be exactly plus 10 and minus 35. And I can actually easily get plus 24 volts because that's what my primary power supply does. And my primary power supply also knocks out minus 12 volts. And so I think we might be able to get away with using plus 24 and minus 12. So that just leaves this question of 150 volts. And so I thought about this and dug through my collection of parts, and I actually have a massive boost up converter. One of those random things I picked up off of Amazon a while ago. And it should be able to take our plus 24 volts and boost it up to 150 volts. And so I think if we have 150 volts coming into the plate, and we'll send it through, of course, a plate resistor, and we measure here, we can get our output, and then we can use plus 24 and minus 12 as our inputs, and we can actually power this up and test it out. So let's go ahead and give that a shot. Of course, there's a problem in that I don't have any way to plug this in. This is a really kind of unique plug. So I thought about trying to push some wires on there and then having essentially an octopus coming out of the back end of this to plug into a breadboard. But I think it might just be easier if I cut up a little circuit board that's kind of like a breakout board for this. So I'll go ahead and design that up in DesignSpark and cut it out in the mill. And well, that all seems to have gone pretty well, and this is my little breakout board here. That looks pretty cool. So I think this might work for plugging into the breadboard. So let's go ahead and plug it in and give it a shot and see what happens. All right, well that breakout board worked perfectly. You can see I've got it sitting on the breadboard here with breakout wires going on. And the way it's split up is that this is one half of the circuit and this is the other half. So we're only going to look at one of these NAND gates. And we'll just know that the other half is identical. And you can also see I've put tubes into our little module here. This is the 6201. Dual triode up top, and then our 6AL5 dual diode on the bottom. And I have my little voltmeter here so I can check some voltages around it. Now for the voltages that we could potentially be checking, I have my big power supply coming in here, and I've got 24 volts coming into this rail on the bottom here, and then ground as well. And then this blue wire is our negative 12 volts. And we're going to use that on these two switches. So these two switches are going to switch between plus 24 or negative 12 going into the two inputs that we had going into one of the NAND gates. Now, this big orange wire here that leads back over to this thing is going to be our really high voltage. You can see it pulls 24 volts off of this rail into here. This will boost it up to 150 volts, which is then going to be going through a 22,000 ohm resistor into the plate of the dual triode here. And then coming off of that plate, we have a 1 mega ohm resistor into a actual neon bulb. So I don't play with high voltage often, and if I'm going to play with high voltage, I want to do it with something really cool. So I've got a little neon bulb here. So that should be our indication as to whether it's working. And now with both of these switches in this position, as soon as I turn it on, the tube shouldn't be conducting. So our plate voltage should be at the high voltage of this. So our neon bulb should come on. And I forgot to mention, we've got a little 6 volt regulator here. This takes the 24 volts off of the main power rail, drops it to 6 volts, and that's what powers the heaters in both of these tubes. Now, well, it should all work. So let's flip the switch on the power supply and keep an eye on our little neon bulb here. But I'll also take some measurements with this, and we'll see what we're getting. So let's go ahead and flip this switch. Oh, look at that. The neon bulb came on immediately. That's awesome. Look at that. Neon bulbs are just so cool. I think they look so awesome. All right, well, I can also see that the heaters in both of our tubes are on and warming up, so that's good. So with the neon bulb on, most neon bulbs have a striking voltage of at least 75 volts. So there should be at least 75 volts on the plate. So let's just go ahead and check that and see what it is. All right, so we've got 147.5 volts on the plate. Now, I don't necessarily recommend running 140 volts through a breadboard. This isn't the safest thing I've ever done, but for the sake of science and experimentation, we'll just tough it out for a little bit here and just be extra careful. All right, so I've got my two switches over here, and right now they're both set up so that both of the inputs are negative 12 volts. Now, if I flip one switch, that should go to plus 24 volts. Now, that plus 24 volts is going to either go through the resistor in here or it's just going to stop at the diode. So we'll just go ahead and flip one switch, and the neon bulb here should stay on. Okay, that's good. I flipped one switch, the neon bulb stayed on. So let's turn that off and we'll flip the other switch. All right, the neon bulb's still on, and I've got one switch. So we've got 3/4 of our truth table done, but the most important one is if both switches are at plus 24 volts. So here comes the moment of truth. The neon bulb should go off when I flip this switch. Yes! Yes, look at that. The neon bulb went off. And then if I switch it off, the neon bulb comes right back on immediately. How cool is that? All right, well, let's check the voltages here. All right, let's, okay, so we've got 147.5 volts. If I flip one switch, that doesn't change. If I flip the other switch, that doesn't change. If I flip both switches, we can see, look at that, we dropped to 43 volts pretty much. So actually, that's really close to what the IBM customer engineering manual was saying of a logic high and a logic low, plus 150 to plus 50 volts. So, you know, this is actually working pretty much exactly how I imagined. That is awesome. I mean, neon bulbs are just super cool anyways, but that's really cool. So I do believe that this is a dual NAND gate. I mean, I could very well be wrong, and if somebody knows, please definitely let me know. I've been losing sleep trying to figure out what exactly it is, but I think I might be onto something here. Now, throughout all of the other episodes that I've done in my channel, there's been one primary theme, and that's I've been avoiding high voltage. I don't particularly like playing with high voltage all that much. So I think what I want to do is I want to pull this circuit apart and rebuild it to see if this will work with a plate voltage of just 24 volts and illuminating an LED. So let's do that. We'll pull all this high voltage junk off of it and rebuild it and see if we can get it working at just 24 volts. All right, so I've gone ahead and redone this, and I've got a 10,000 ohm resistor as our plate resistor. So that comes off of 24 volts here and goes into the plate. And then I'm using a 22,000 ohm resistor as our output. So this comes straight off of the plate, goes through this 22,000 ohm resistor, and then goes into our green LED here. And then I've got another 10,000 ohm resistor in parallel with the LED to create a voltage divider to make sure that when this is at logic low, the LED is off, and then when this is at logic high, the LED is on, but you know, we don't explode it. Now, I did just hook this up. I haven't tested it yet, so if the LED explodes, well, at least it'll make for some interesting footage. But let's go ahead and turn the switch on and see what happens. The LED should come on. Okay, well that's a good sign. The LED did come on. We'll let the tubes warm up just a little bit here. All right, let's give this a shot. Let's flip one switch. The LED stays on, that's good. Let's flip the other switch, the LED stays on, that's good. All right, now let's flip both switches. Hopefully this LED will go off. Oh, it didn't go off, but it got a lot dimmer. That's good enough for me. That means it's working. That's awesome. So I should probably work on my voltage divider setup here a little bit, but I mean, we very clearly have a logic low and a logic high going on. It's just our logic low is still high enough that the LED turns on, and the LED is pretty sensitive. But you know what? I'm actually really happy with that. That's awesome. We've got it working. So I tell you what, let's take a look at the voltages on the plate and see what we get. All right, I've got my voltmeter set up here, so I'm just gonna measure directly on the plate right here. All right, so we've got 17.3 volts. It's actually not as fantastic as some of the NOR gates that we created earlier, but you know, this is designed to work at 150 volts, and it worked fantastically at that. So I'm actually surprised that it's giving us a logic high that close to 24 volts off of this. Let's start flipping switches and see what happens. All right, that's good. We don't change there. All right, with both the switches, if we flip just one switch, we're rock steady, and that's because of the way that this diode resistor NAND gate is set up. Let's flip both switches and see what we drop down to. 8.46 volts. All right, so we can see that's why our LED doesn't exactly go dim, but we're getting, you know, a 9 volt swing out of that. That's awesome. Look at that. So this IBM module is extremely well designed because it works on such a wide voltage range. I mean, it was designed to work at 150 volts, and we can see that it's operating, not fantastically, but it is operating at just 24 volts. This is awesome. What a brilliant way to make a NAND gate. That is super cool. I'm super excited and happy with the way that this turned out and the way this works. And you know, I think it is a dual NAND gate. That's my guess. So out of all of this reverse engineering and studying and guessing that we've done, I'm going with dual NAND gate. But if somebody knows, please let me know. I would love to see some documentation or even just some more pictures of one of these. I think this thing is super cool. I'm also really happy with the way my breakout board worked on the bottom here. So this actually will work with pretty much any one of these IBM modules. And there are a ton of different modules that all use this same plug on the bottom. So if in the future I get my hands on another one of these modules, we'll take a look at it, see if we can figure out exactly what it is, how it works, and then again, we can plug it into a breadboard and experiment with it. That's awesome. A piece of computing history right here, functioning both at the voltage levels it was intended to and at the voltage levels it was absolutely not intended to. So in the next episode, we're gonna move on and take a look at something totally different. But in the meantime, I'm gonna see if I can find a place to mount this in my room. I think it's just such a cool looking piece of technology that it really needs to be on display.